Good afternoon, everyone. Please raise your hand if you do not know anyone who has probably contacted dengue. Probably none, right? I mean, of course, except that only Mary and me are in this video recording. But I believe, regardless of what generation you came from, you are subconsciously aware of the presence of dengue. Hence, moving forward, this is Josh and my partner Mary, and we will be presenting our project tackling this disease entitled Climatologically Driven Temporal Predictive Modeling of Dengue Cases in the Philippine locations. So for a more technical background, endemic in more than 128 countries, and for the Philippine in the Philippine context, in 2019 alone, around 24,000 deaths was tallied that are related with dengue, signifying it as a major health concern. But despite this, even with the availability of prevention methods such as vaccine, the Vaccine Confidence Project in the country has highlighted a concerning decline with the public opinion in dengue vaccines plummeting from 93% in 2015 to a mere 32% at present. Hence, to achieve the zero target deaths and minimal cases, recently presented in the 2023 Dengue Summit in Thailand, attended by 51 countries, including the Philippines. They have highlighted the great importance of fostering mutual collaboration between various institutions and sectors to strengthen the dengue-related programs implementation. Hence, the idea of this project to be part of this collaboration.
Recent local studies have established the critical role of climate factors such as rainfall, temperature, and relative humidity in predicting dengue cases. These studies confirm that variations in these climatic elements significantly impact the incidence of dengue. Building on this knowledge, classical machine learning models with various feature combinations were employed to forecast monthly dengue cases in multiple studies. As done by Adao et al., among the different models tested, the random forest model demonstrated the highest performance with an R squared value of 0.5654. And this suggests a correlation between the predicted and actual dengue cases, showing the potential of machine learning in this domain. Additionally, studies focusing on other countries have shown how climate variables can be effectively used to predict dengue cases in their domain. These examples establish that a climate based machine learning model can be adapted to our local context here in the Philippines. With that, our goal is to expand upon these findings and address the challenge of dengue cases here in the Philippines. So we aim to develop a robust predictive model for dengue cases within clusters of cities in the Philippines. By focusing on these clusters, we can account for regional climatic variations. Utilizing machine learning and time series analysis, we will train on climate data. This will allow us to understand the temporal patterns and trends in dengue cases and climate data, further refining our predictive capabilities. Finally, leveraging the forecasted dengue cases, we will establish guidelines to identify potential outbreak zones. This proactive approach will enable us to predict cities at risk of outbreaks, facilitating timely interventions and resource allocation.
So for our methodology, we have decided to divide our main process into these five major subcategories. So basically, the discussion of our data set, what we will focus our study at, the feature processing steps that we take, the modeling part, and how we forecasted the dengue cases and outbreaks.
So the number of dengue cases were obtained from the Department of Health in the Philippines as weekly data covering the period from January 10 to 2016 to January 10, 2021. In particular, we cut off January 10, 2021 to only limit to 2020 data. On the other hand, the climate variables were web scraped from the NASA prediction of worldwide energy resources or power project. From the web scrape data, we have selected a comprehensive set of climate variables that are likely to influence the spread of dengue. Studies have shown previously that temperature and hydrological variables such as humidity and precipitation affects mosquito development, survival, and the incubation period of the virus within mosquitoes. Another study also showed that wind speed affects mosquito flight patterns and their ability to find hosts, thereby influencing transmission dynamics. Meanwhile, solar radiation and cloud cover can affect the temperature and hydrological variables, which are found to have a significant influence on dengue prediction. So now that Now we will discuss the steps taken to handle these data. Firstly, we perform web scraping to collect climate data, where this was done per location and per day from January 10, 2016 to January 10, 2021. Once the data was collected, the next step was the aggregation process. So we calculated the mean, maximum, and minimum values of the climatic variables for every week of the time period to standardize its granularity with the weekly dengue cases. We also filled the null values that showed gaps between the weekly time series data for the dengue cases. We then performed a stationary check on our data. Stationary implies that time series is stable and predictable, which are crucial for building predictive models like ARIMA. So we used the augmented Dickey-Fuller test. So some of the test results, particularly on dengue cases, as shown in the graphs on the right, display the test statistics on the p-values for locations such as Bulacan, Rizal, and Quezon City. And based on the ADF test for the dengue cases variable, the time series data for these three cities were deemed stationary because the test statistics were less than the critical value at all confidence level with p-values less than 0.05, leading us to reject the null hypothesis and showing that the results indicate the dengue cases for the three cities is stationary. We also performed a stationary check on our climate data, which we found to be stationary as well, suggesting that its statistical properties does not change over time.
So, as initially mentioned, we decided to limit the focus of our study given its very large amount of data and high dimensionality, on top of the consideration of the regional climatic factors. We have opted to focus the limit of this study on just a few locations in the Philippines by performing the PSNE plus K-means clustering in a single pipeline optimized by Optuna, maximizing the silhouette score. So on this run, we were able to obtain a 0.42 silhouette score with these parameters and had 28 clusters of locations. So for the study, we just arbitrarily chose which clusters we will focus on. So we resulted to the cluster including the Bulacan, Quezon City, and Rizal. For our as part of our feature processing and engineering, so we did the DB scan to detect the anomalies. So with the grid search as hyperparameter search to determine the number of points that may be considered as outliers. Intuitively, spikes in dengue cases as seen in the graph were identified as anomalies. So to consider this in the study, we added this as features, categorical features, indicating whether a point is 1 equal to normal or -1 if it is anomaly. So we also added some other features such as moving average and Fourier transform for our features. Given the very large or high dimensionality, we initially performed feature selection by univariate correlation check. So we set the threshold to 0.95 and filtered our data. So we resulted to 40 features after filtering from 59 features.
So we selected the best model for our time series analysis using AutoArima. So this is an automated process that helps us find the optimal ARIMA model by tuning its parameters. So we focused on two specific models, SARIMA and SARIMAX. So SARIMA, or the seasonal autoregressive integrating moving average, extends the traditional ARIMA model by incorporating seasonal effects. On the other hand, SARIMAX, seasonal autoregressive integrated moving average with exogenous regressors, builds on the SARIMA model by allowing the inclusion of external variables that might influence our time series. So for both SARIMA and SARIMAX model, we define the following parameters or ranges for the parameters in this slide. In our methodology, we utilize TPOT to evaluate a variety of the models shown in the slide. So the models that were surveyed and the parameters that were tuned for each are shown here, where we particularly highlighted some of the models that we were ran. SGD regressor, which uses a stochastic gradient descent for regression tasks, while XGB regressor, which is an implementation of gradient boosting with additional enhancements.
As initially mentioned, we have wanted to have a use case for our project. So we decided to use this latest WHO Technical Handbook for Dengue Surveillance to identify the weeks as outbreak. This is basically just a calculation of 3 4-week moving average plus 2 standard deviation of the 4 weeks prior to the time t.
So, as said before, we evaluated several models and optimized their hyperparameters for to achieve the best performance with AutoArima for Sarima and Sarimax, while Aptuna for XGBoost and SGD regressor. So let's go through the models and the results for predicting dengue cases, specifically in Bulacan. So the seasonal or the Sarima showed minimal explanatory power as indicated by the very low R squared value of 0.02% and a high RMSE of 151.75, suggesting poor fit and high error in the predictions. As for Serimax, it has significantly improved in performance with a high R squared value of 79.38% and a lower RMSE of 68.29 compared to Sarima, which indicates a much better fit of the data because it includes the exogenous variables of climatic data. The extreme gradient boosting model demonstrated strong performance as well with a high R squared value of 72.93% and a relatively low RMSE of 78.23, showcasing that it also works effectively. Lastly, for the stochastic gradient descent regressor, it exhibited the best performance among the models with the highest R squared of 85.10% and the lowest RMSE of 52.07, indicating excellent fit and predictive accuracy. So, in summary, while Sarima did not perform well, Sarimax, XGBoost, GB regressor, and SGD regressor showed substantial improvement, with SGD regressor leading in overall performance.
In conjunction with the results that Mary presented earlier, we have also obtained these Paris plots showing the actual versus predictions of the models. It is highly visible how poor the Sarima performed, signifying the need for the necessary time series pre-processing steps that we actually opted to skip. It could also be seen that the time series plot, unlike for SGD and Sarimax, which was able to predict the possible spikes or increases in cases in the testing set, which is more pronounced actually in SGD. XGBoost has overfitted, showing its poor performance in predicting sudden increase in the target. Additionally, data points were classified as based using that set threshold that we defined earlier. Unfortunately, we have misclassified on most weeks with some points which shown as outbreaks even though they're not. What we have gained here is that outbreaks are generally not equated to case spikes, as some have gradual increase as shown and may require more complex features to predict, unlike the cases.
So, to conclude, we developed a climate based model to predict dengue cases within the same cluster of locations in the Philippines. So, this model takes into account various climatic factors to provide accurate prediction. Wherein, in our analysis, we found that SGD regressor yielded the best predictive performance. Specifically, it achieved an R squared value of 85.10% and an RMEC of 52.07 for predicting the number of dengue cases in Bulacan. So the data obtained from the study was utilized further to apply existing guidelines and forecast the possibility of dengue outbreaks in specific locations. So with this, we can help in better preparedness and response to potential dengue outbreaks.
So considering the results that we obtain, we recommend the following. So first is that perhaps more features, including population, demographics, access to healthcare, and city index, may be used to obtain better predictions for cases and perhaps for outbreaks. Additionally, we may explore spatial dependencies, which could give better generalized model in predicting locations that they are not trained on. So you possibly through spatial interpolation and using uh, some more deep learning methods such as LSTM with attention-based mechanism. And lastly, we could also try to use the dengue prediction to other machine learning problems such as hotspot detections and perhaps outbreak classification. So rather than predicting the number of cases, we could predict the labels such as whether the city is experiencing outbreaks or not. So that's all for our presentation. Thank you very much.